For this video, we're going to talk about how we make measurements of the density of gases. So, not OG, of gases. So as a reminder, density is related to mass per volume. So density in general is mass over volume. For a gas, and this is important, our unit is usually going to be grams per liter. Notice this is different than the density you tend to use for liquids, which tends to be grams per milliliter. And that's because gases are much more spread out. So it's not a rule that you absolutely have to. No, gas only has one S. I don't know why I gave it a second S. So you could report densities in grams per milliliter, but they're going to end up really tiny. And even as grams per liter, they'll still be pretty small. So this is going to be something that this is just to give you an idea. So this is something we tend to do, and it's the unit we tend to use for it. Another useful note is the last video we talked about the idea of STP. So in general, the volume for 1 mole of gas at STP is going to be 22.4 liters. So this lets us actually convert directly from moles to liters without having to use the other part of the PV equals nRT equation, so it can be a useful conversion sometimes. So the important thing with density, though, is density is related to mass, not number of molecules. So that means different gases are going to have different densities, even if they have the same number of molecules in their container, that we can still end up with a different mass. So not gases with different numbers of molecules or the same number of molecules are going to weigh different amounts. So for example, if you were to calculate the density for helium at STP, you're going to find that it's 0.179 grams per liter. And the reason for that showing the work is its molar mass is 4 grams per mole, and its volume is going to be 22.4 liters per mole. On the other hand, let's take nitrogen. And this time I'll show the work up front rather than showing it afterwards. It has a molar mass of 28.02 grams per mole. But it's still going to have the same volume per mole, 22.4 liters per mole, if you're at STP. That means it's going to have a density of 1.25 grams per liter. So our nitrogen is going to weigh significantly more than our helium, even though both are going to weigh very little. If you think about 1.25 grams, that's telling you if you had a 2-liter bottle, you'd have 2.5 grams. That's the weight of like 2.5 paper clips for a 2-liter bottle filled with nitrogen. So gases are pretty light compared to liquids and solids. Now, this is specifically at STP. It's pretty easy to do, but we can generalize this equation that the density of a gas is going to be equal to, let me make sure do I like this wording? Yeah, that's one I like. The pressure times the molar mass divided by the gas constant. I'll write words and then I'll put variables next. The gas constant times the temperature. So D equals pressure times, I'm going to write molar mass out, and I'll talk about why in a second. Gas constant R, temperature T. This molar mass here is sometimes written as like a cursive M, which I wrote pretty badly. That looks more like a U from micrometers, right? I'm really bad at writing my cursive M. If I'm typing it, it's one thing. But my ability to write we're going to try. I suck at it. I'm just bad at it. So if you have really pretty calligraphy and you can make your molar mass look nice with this M symbol, or you have a computer where you can type fancy M, that works fine. I have a problem that I've found that my students will sometimes put molality in there instead, even if it's not related and we don't have a liquid concentration, or they'll get bothered by it. They'll be like, this should be molarity. I don't know the molarity though. And so that causes problems. So I just put the word molar mass. I find it easier. And I don't like using MM because we don't use 2 letters to represent variables. So because then it could look like, oh, it's molarity times molarity. It's molarity squared, which wouldn't make any sense here. So I like to report just D equals P times molar mass over RT. So this means we can plug some values in and get density. So let's do some practice with this. I will also point out, I've shown you an ideal gas law and I've shown you this density law. They're both true statements and they're both useful. You will use the ideal gas law a whole lot more than this one. I'll fully admit it. But I do think it's still useful to know this one, and you should practice it some too. But you're going to get to the point where the ideal gas law, I hope you can do it in your sleep. You've done it a whole bunch of times. This one, you might have to look at something to remind you, okay, wait, what's the equation for this? How do I do this? But they are related to each other. You can actually use the ideal gas law, plug in some values, and find out how you get to density if you'd like to. I've decided I used to do that with students, and then I found out they just didn't care about where it came from, so I stopped showing that part. But I do think it's interesting. I'm happy to talk about it in office hours, for example. I can show you, hey, here's how I got through that. So let's take an example problem. So we're going to calculate the density of nitrogen gas. We're going to put it at 125 degrees Celsius, so not STP, and at a pressure, oh, my hand got itchy, which messes with my ability to write, and a pressure of 755 millimeters of mercury. And Dr. Leslie has realized he gave himself very little room. We're going to see how this goes. Don't want to erase the slide, though. So now, you'll notice this is not in the units we usually use. So we have to start by doing some conversions. So let's start with our temperature. So temperature, if it's 125 degrees Celsius, and we add 273 to it, or you can add 273.15, they both work, we will get that this is 398 Kelvin. The reason why I didn't do the 0.15 is we don't know it to the decimal anyway, so we don't know it that accurately, so 273 made the most sense. Now pressure, we need it in atmospheres. So we have 755 millimeters of mercury. What we know is that 760 millimeters of mercury is equal to 1 atm. So it's almost an atmosphere, but not quite. So let's see. That will give us 0.993 atmospheres. And our molar mass, so they didn't give us a number directly, but they told us it was nitrogen gas. Remember, nitrogen is a diatomic. That means it's going to be N2. One nitrogen weighs 14.01 grams per mole, so the molar mass is going to be 28.02 grams per mole. And hey, they gave us everything we need. And now it's in units that match up. So the density is going to be equal to 0.993 atmospheres times our molar mass of 28.02 grams per mole. And we're going to divide it by R 0.0821 liters times atmospheres per mole Kelvin. And then we have our temperature, which is 398 Kelvin. If we check our units, our Kelvin cancels, our mole cancels, and our atmosphere cancels. And we're left with grams on top and liters on bottom, which matches what we said density tends to be, grams per liter for gases. 0.993 times 28.02 divided by 0.0821 and divided by 398. And if I do that, I get the density, once I find my marker, there's my marker, is 0.852 grams per liter. So that's an example of how we can solve questions like this. So a big hint was it asked us for the density of our problem. Now let's look at one second example that's worded a little differently. So let's say we know this. A sample of gas has a mass of 0.311 grams. Its volume is 0.225 liters at a temperature of 55 degrees Celsius. And a pressure, these problems we have to tell you all kinds of variables as you notice, and a pressure of 886 millimeters of mercury. Find its molar mass. So I'd like you to give this problem a shot, and just because I don't want you to just pause and give up, if you don't see, well, if you already see how to do it, pause me and just try to solve it. But if you're not sure, I'm going to add one more thing now. So if you've already know how to do it, pause me and go. Density, remember, is grams per liter. So while I don't give you the density, you can find it. Try using this, find the molar mass of this substance. So I'm going to give you a chance, pause it, try it out. Okay, so hopefully you did that. Now, depending on how you tried to solve this, I want to point out that there are two ways to get here. I'm going to use the equation we just looked at, and that's what I know many students do because they see, oh, you just showed us a density equation, let's use that. So density equals pressure times molar mass over RT. However, this isn't the only option. You could have used your PV equals nRT and solved for moles, and then grams over moles gives you molar mass. So if you did that, congratulations, that works too. I'm not going to show that way, but it works perfectly fine. And that's one of the realities of equations in chemistry. Sometimes you can use more than one thing to solve the question because they all get you to the right place as long as they aren't making any assumptions that aren't true in your setup. So that's really the main thing that comes up of why you might use one equation over the other, is one might make certain approximations that others don't. But if there are no special approximations being made, you can use different ways to solve the same problem, and you're perfectly fine. So now we need to rearrange this equation. We want to find molar mass by itself. So I'm going to start, I need to multiply both sides by RT to get it out of the denominator, and I need to divide by pressure to get it out of the numerator. This is going to lead to dRT over P equals the molar mass. So just to show, I don't think you need to show this every time, I multiplied by RT over P on both sides. And what that did is this pressure on bottom cancels this one on top. This RT on bottom cancels this one on top. So that's how I picked what to do. I went, I need to get rid of the RT and the P. So I used the inverse of it. And I have to multiply on both sides so that nothing gets changed overall. So now we can plug in what we know. So the density is going to be, so let's find it to the side, density is 0.311 grams per 0.225 liters. So if we plug that in, divided by 0.225, I'm going to get that it has a density of 1.47 grams per liter. So we know, and I lost my pen again. Sorry about that. 1.47 grams per liter. R is a constant, so it doesn't change. It's 0.0821 liters times atmosphere per mole Kelvin. Well, then we get a temperature. Ooh, I got to solve that one too. So we have 55 degrees Celsius. But if we add 273, we turn it into Kelvin, and that'll be 328. Right? Yeah. 328 Kelvin. And the pressure, again, we have to do another conversion. We have 886 millimeters of mercury, which also could have been torr, since they're the same thing. And we have 760 millimeters of mercury is 1 atmosphere. So we have 886 divided by 760, and we will get 1.17 atmospheres. So we put that down here, 1.17 atmospheres. The atmospheres cancel, the Kelvin cancels, the liters cancel, and we're left with grams in the numerator, moles in the denominator. And hey, that's the unit for molar mass, so that's good. And so I'm going to plug all this in. And when I do that, I get that this has a molar mass of 33.8 grams per mole. So that's the molar mass I would get for my compound. So this is another way the question could have been worded that would ask you to use that. And while it didn't directly give you the density, you could easily find it since it gave you a mass and a volume. And again, this problem, some of them can't be, but this one could have been solved using PV equals nRT. The last problem, that wouldn't have worked as well. But for this one, if you used it and you got the right answer, that's A-okay. So just use whatever ends up working out best for you to help solve these. And with that, that concludes this area on here. The next idea we'll be going into is we'll start working with mixtures of gases. So everything so far has been single gases, but we'll start working on mixtures following from this. Because obviously, as chemists, we're going to want to mix things together because that's how we make chemical reactions. Plus, lots of gases come as mixtures. For example, the air you breathe is made of not just one gas. It's not just the oxygen you need, but it's got lots of nitrogen in it and some carbon dioxide and then some other stuff. So how do we deal with that? That's what we'll be working on next.